Hi, today I'll be talking about a synthesis-aided compiler for DSP architectures, or digital signal processors. This is a work-in-progress paper from me, Alexa Van Hatten, and my collaborators at Cornell, UT Austin, and Facebook Reality Labs. So to start with, what are the overriding design constraints that DSPs optimize for? So as you can see from these applications across embedded augmented reality, virtual reality, mobile sensor processing, and computer vision, it's really important that DSPs support battery-backed computation, so they need to be energy efficient. In addition, they need to support real-time computation with low predictable latencies. And in order to meet these design constraints, DSPs tend to have custom instructions. Think exotic vector instructions and VLIW or very long instruction word instructions. These instructions oftentimes require expert tuning to get the best performance, whereas a traditional CPU may rely on technology like out-of-order execution in order to expose parallelism at the architecture level. DSPs tend to expose parallelism through the programming model itself. So you either need an expert to tune them to use these custom instructions, or you need a compiler that is intelligent enough to do that same job. So I'm calling out that there's this kind of spectrum where on the left you have faster compilation that has less aggressive optimization. So this is where traditional compilers tend to sit. They want to run on full large-scale applications with potentially millions of lines of code, so their compilation needs to be fast and therefore not always find every last drop of optimization in their analysis. I would argue that DSP kernels sit further on the right, where compilers for DSPs can actually spend more time in compilation in order to have more aggressive optimization. In particular, DSPs tend to have smaller and oftentimes fixed size kernels, and so it's easier to have a more aggressive and potentially longer running analysis in the compiler to get the very best on-device performance. So traditional compilation techniques like loop analysis-based vectorization are going to be here on the left, where they use a kind of series of rule-based translations that can run fairly quickly and find individual optimization opportunities, but might miss some kind of global or overriding optimization opportunities that are harder to find. The question we ask in this paper is whether we can use a programming language technology called program synthesis to generate kernels on the right. So rather than being a series of rule-based transformations, program synthesis is instead generating a search space of programs and using search strategies to find programs within that space that meet design goals. So let's look at a concrete example. 2D convolution is a ubiquitous kernel in embedded machine learning applications, and we have a filter matrix that slides over an input matrix, and the output matrix is going to consist of a element-wise sum of products of the overlapping elements. Now let's look at why this poses some challenges for traditional compilers. First of all, we have a simple kind of loop-based kernel here of a deep loop nest, some predication, and then writing to our output element. The first challenge is going to have to do with vector width alignment. So if we have a vector width of 4 or 8, the innermost loop has a loop bounds of 3, and that doesn't kind of evenly divide our vector lanes, and so even a simple unrolling strategy is not going to have full vector lanes of computation. Next, we have that there is this if statement in the loop body, so we might be able to tackle this particular instance of control flow by using predication in our vector instructions, but even then, the predicated elements are still going to have kind of missing computation. And this is especially important in DSP kernels where a small matrix size means a higher percentage of elements are on the edge of the matrices, so that kind of cost of predication is more prominent. Finally, you'll see that the access expression for the filter matrix is from a computation to calculate the transpose, and this means we have potentially non-contiguous memory access, which is harder for a compiler to reason about. So let's look on the other hand how we might hand tune a kernel to target 2D convolution based on our specific DSP ISA. So we start by having loads and stores to vector registers, and then we might use a vector multiply accumulate or vector MAC based on the pattern of products and sums in this particular kernel. To get around the challenges in alignment and data movement we saw previously, we might use an ISA-specific shuffle instruction. What this does is takes an input vector register as well as a static register of indices and uses those indices to select the corresponding elements of the input. So here we would take the second element twice and the third element twice. The overall idea in this paper is using sketch-based program synthesis to find optimal data movement. Sketch-based synthesis is where you have a sketch or template that constrains the search space of the synthesis formulation, and then the synthesizer's job is to fill in holes in that sketch with expressions that make the overall program correct up to some specification. And we've implemented this in a compiler that we call Diospyros. So to get into detail, we first take in an architectural description, which includes available functions and the vector width, and then a reference implementation. This is in a domain-specific language, or DSL, that we have embedded in Racket's Rosette framework. Here you can see the the spec for matrix multiply, which uses a simple imperative pattern to apply plus and multiply over the matrix elements. Next, we have a sketch in the same vector DSL. This is parametric over finite instance sizes, meaning you can define one sketch for multiple different problem sizes. And it has symbolic holes, here represented with a double question mark, that need to be synthesized. You can see on the right for the sketch for matrix multiply, we have holes for the exact shuffle indices, as well as for which register of the output to write to. Next, where a lot of the magic happens is in the data movement and compute synthesis. So we discharge to an off-the-shelf SMT solver or satisfiability solver, either Z3 or Boolector currently, and we do an iterative search based on a cost model to find the solutions that are both correct and have the lowest latency. Finally, we have a straightforward code generation pass that emits executable C or C++ and DSP intrinsics. So let's look at how this works for our concrete example. If we look at just the first register of output in our 2D convolution, this is what running our reference implementation gives us, a mathematical specification of the output. It's quite complicated, but I just want you to look at the first product highlighted in red. Here are the elements that this uses in F&I. In order to have 4 full vector lanes of computation, our sketch will have 2 vector shuffles that feed into a vector multiply accumulate. Diospyros' search will then fill in the exact shuffle indices, as well as the exact register of the output that we need to have a correct and fast implementation. This will be repeated across the products in this register, as well as across the registers of the output, to give us a full kernel. Now, let's look at how Diospyros actually performs in practice. So here we have a preliminary evaluation of our prototype that targets Cadence's Tensilica Fusion G3 DSP. On the left axis, we have cycles from the cycle level simulator, and on the x-axis, we have various input sizes. So first, we have a naive loop-based kernel as shown previously, both with parametric sizes and with inlined fixed sizes. You can see that in the fixed size case, the default compiler at an O3 optimization level is able to enroll more aggressively for faster code. Next, we have the vendor library. So this is a commercially available library that ships with the Fusion G3, and it targets ISA-specific instructions, just like Diospyros. And finally, we have Diospyros, which is about 7 times faster than the vendor kernels. And this speedup comes partially because Diospyros is able to produce fully straight-line code without any control flow, and it's able to almost always have 4 full vector lanes of computation. Now let's look at how we compare to an expert written kernel. For matrix multiply, we have an expert kernel that predates Diospyros. It presumably took an engineer days or even weeks to write this kernel, but it is much faster than the other baselines. Diospyros, however, in only 9 seconds of synthesis, is able to find a solution that is within 20% of the expert kernel. If we let Diospyros run for 30 minutes of compilation time, it bridges this gap even further, finding a solution that is nearly as fast. Because this is a work in progress, I want to leave you with some of the ongoing work that we have. So because sketches currently require some expert knowledge to write, we want to work towards programmability of these sketches, making it easier to generate sketches automatically. Next, like many program synthesis projects, we have a lot of work to do in terms of scalability, so we're working on various problem decompositions in order to scale to larger kernels. And finally, while we currently target a single DSP, we would like to have target independence to be able to take in various architectural descriptions and target multiple DSPs. Finally, I want to leave you with this key idea, which is that program synthesis can unlock efficient data movement in DSP kernels. Thank you, and I look forward to your questions.